So let's go ahead and get started. Sorry we're starting a little bit late. Always, when working with technology, there's little hiccups that can occur. So today what we're going to be doing is we're going to be talking about projectile motion and more specifically two-dimensional motion. So in order to do that, what we're going to do first is we're going to have some concept-driven questions, and then at the very end we're going to be moving into some calculations. We're going to continue on with some of the calculations next time. But just to kind of give you an idea of the direction that the calculations are going to go, say for instance I have some object and it can move in 2 dimensions, and we can say that this position of this object can be parameterized by 2 coordinates, the x-coordinate and the y-coordinate. So at every point there's going to be some x of t and some y of t. Okay? And associated with that is also an equation for the velocity in both the x and y direction. So ultimately what this means is we're going to describe this motion by saying that there's pairs of equations. Instead of, like we said last time, we just had some x of t is equal to x0 plus v0 t plus 1/2 a t squared. Now there's also an associated y equation. So y of t is equal to y0 plus v0 t. Well, in principle, these should be different. So this is v0x, v0y, plus 1/2 a sub y t squared. And then some velocity equations. So the velocity in the x direction, this is the v0x plus a sub x t, and v sub y of t is equal to v sub 0 y plus a y t. Okay, so really this doesn't add that much to what we've said already. I mean, in some sense it does because it doubles the number of equations, but the way that you use them is exactly the same, right? Because we know how to deal with just this. And now what we're going to say is there are things that can happen in both the x and y direction, but they're decoupled in the sense that what happens in x stays in x. What happens in y stays in y. What happens in Vegas stays in Vegas, right? Okay. So we're going to get more into the concept-driven questions. But kind of bear this in mind when you're thinking about these concept questions, because eventually we are going to be coming to the equations. Okay. So, first question. The following objects are dropped from the same height. Which one falls to the ground first? And we have a basketball, a golf ball, a bowling ball, and a marble. Okay. Okay, so let's talk about this one. What do we think? What do we think? How about you guys? Yeah. E. Why E?
Because like they're all dropped from the same height and they're all going to reach the same acceleration at the same time.
Right. So all of these objects, regardless of their mass, are going to have the same acceleration. So if you drop them from the same height, it's going to take the same amount of time for them to fall. Now the addendum to this, and if you think about more complicated systems, we tend to look at the most simple system. So in our class, we completely neglect air resistance. But you notice that if I drop a feather, or drop a bowling ball, very obviously the bowling ball is going to fall faster than the feather does. And we're going to talk more about forces later in the semester, but ultimately there's some force due to air resistance. That particular force we won't talk much about, but there are some approximations that we make, and you'd actually see that if you can get rid of the air, so if you do this in a vacuum chamber, there's actually a video online of there's some like old Soviet missile silo that they converted into this giant vacuum chamber. So it's like, you know, it's probably many times the diameter of this room, and it's this giant vacuum chamber. And what they did was they released a feather at the top, and they released a bowling ball at the top, and they actually hit the ground at the same time. But it's only when there's no air resistance. Okay, so this one is indeed they will hit at the same time. So the next one, a blunt object is tossed horizontally at the same moment that another object is dropped. Which one is going to hit the ground first? Go ahead and talk about this one. Okay. So let's talk about some of the ideas we came up with. So somebody from the back, middle, what do you think? What do you think happened? The hat.
I said they both hit the ground at the same time.
Why?
I don't know. They both had the same bullet.
Okay, sure. That's one idea. Any other ideas? Yeah.
X and Y are independent.
X and Y are independent, yeah. Anybody else? Okay, well we have a video to see exactly what happens here.
The misters are testing a real doozy.
Everything's hot, ready to go.
Bullet shot versus bullet dropped. But a malingering magnet is holding up the show.
As soon as it's released, it's just staying there.
But do you think Adam's going to let something like that stand in his way?
Awesome, that works.
Oh no.
So, the electromagnetic is gone. It's on the scrap heap. We've got a new little solenoid in there which will whoop, get out of the way and let the bullet drop. All we got to do is try it once, get our timings right, confirm them, and we should be ready to do this test.
So the new simultaneous release system is ready for a test fire.
All right, simultaneous release in 3, 2, 1.
All right, let's see how it did on high speed.
But once again, there's a timing problem.
Solenoid's way too slow.
Yep.
It's not letting go.
The most difficult thing about this whole experiment is getting the fired bullet and the dropped bullet to become airborne at exactly the same time. And we can't tolerate even a few milliseconds of variation in this mix to make the result that we want to see happen. It's hard.
Now there's an understatement. So cue the brainstorm.
We're not even seeing the pin start to move.
It gave us the problem that we currently have, which is that it's late.
Having spent the past 4 hours trying to sort out the solenoid,
Look, let's do this twice.
the boys are now staring failure square in the face.
And all it is about figuring out some way to mechanically push between these two.
Until Jamie snatches victory from the jaws of defeat.
You have a hinge that you pull in the middle.
Yeah, that's what I
There
mean.
needs to be some sort of a little bitty catch that is on its edge. I could make a clip like that.
He adds a small metal clip to the trigger to delay the gun the minuscule milliseconds needed to match the solenoid.
Everything's hot, let's do it.
And after a few test fires and a bit of fine-tuning, it works.
Bullet bead done. Oh, it's good. It's good. It's 1/3 of a millisecond difference.
Wow.
That's freaking perfect. Let's go do this full scale.
Okay.
Which means rolling up the room 360 feet to stake out a drop zone.
Right about there. That's where they were landing out in the shooting range, so this is where I expect them to land here.
Okay.
Adam lays down a runway of white paper so the high-speed camera will clearly see and measure both bullets at the same time, in the same place, and in the same shot. All we need now in the drop zone is Jamie's drop rig, so the boys can take a shot at physics history.
All right, dude, you ready to do this for real?
I think we'll hit it on the first shot.
Really?
Oh, yeah.
You never make predictions. That's awesome.
Bullet dropped versus fired. In 3, 2, 1.
But from 360 feet away, the boys can't see exactly where the fired bullet landed.
Let's go see where it hit.
So Adam takes a one-wheeled ride down the room to check out the drop zone.
Wow.
And the results are simply ripping.
Can't get much closer than that. Ugh. I can't wait to see the high speed. So, dude, this bullet carved a streak right under the drop zone. I think this might be the shot we've been looking for.
In real time, it's impossible to tell what happened until Adam analyzes the high speed and crunches the numbers.
3677 minus 3915 equals 238 divided by 6. Dude, the difference is 39.6 milliseconds.
Which means it's less than the human eye can make out.
So after days of brain-teasing tests, the Mythbusters can claim a world first for themselves and a victory for physics.
Let me put 39.6 milliseconds into some perspective for you. When you go to the movies and watch a projected celluloid film on the screen, you know that that film's made up of individual images, right? What you might not have known is that it takes 24 of those per second to make up the film that you're watching. So each one is on screen for exactly 1/24 of a second, but you don't notice that because it's faster than your eye can register. Well, that 1/24 of a second is actually longer than 39.6 milliseconds. That's how close those two bullets were.
2 bullets, one dropped, one fired. Amazingly, they ended up in the same place at the same time.
Dude, this myth was every bit as much fun to test as I was hoping it would be. And I gotta say, even though the physics textbooks had it right, I love the fact that we did it full size with real unmodified bullets. I bet no one has ever tried that before.
I think you're right. And whether it was ball bearings or bullets dropped or fired, they all hit the ground at the same time.
Yep. Gravity, man. It's not just a good idea, it's the law. Confirmed.
Confirmed.
Okay. So the next question says, 2 rocks are tossed horizontally and the resulting motion is traced in the diagram shown. What is the best explanation for the difference in trajectory? So we have this rock A and rock B. So go ahead and talk to each other about this one.
Are these blocks with the same?
So think about it. There's a difference in their trajectories, but I don't tell you why there's a difference. So you want to think about why the difference is there, right? Because this was probably related to the problems I was having to start with. What can cause the rock to accelerate?
If it's moving in the same direction, like same sign and on X and Y, then it gains acceleration.
Right, so there's actually, and we're going to talk a little bit more about this when we get to forces, which is the next topic. Forces are causing acceleration. So then you can say, well, what forces might act on this? Well, there's actually only one. Yeah.
Gravity?
It's gravity, right? So if gravity is the only thing acting on this, that's the only thing that can cause acceleration. And so because of that, gravity is always acting down, or more specifically, it's always acting towards the center of the Earth. And if that's the case, then both of these objects actually have the same acceleration, if they have the same mass. So and actually even independent of being the same mass. So it can't be that the 2 rocks have different accelerations. But what we can say is that rock B has a larger initial velocity than rock A. And we can see that even when we look at these equations. So if we say that the only acceleration that you have is the acceleration in the y direction, that means that in the x direction for both of these, there's no acceleration here. And we could also even say that their initial positions are the same, right? Because they both start, we can say, at 0. And we can say, well, the only acceleration we have here is the acceleration due to gravity. Let's put that in here. And so what can change how far it goes when we look at this equation? Well, it takes the same amount of time for it to fall for each one of these. And so the only thing that can be different between these is the initial velocity that each one of them have. And so the initial velocity for B is larger than the initial velocity for A. Okay, and we're going to run into some problems if... What did I do last time to fix this? I switched it to the dock cam. Well, one way I could do this is to turn my laptop and put it on the dock cam. I'd prefer not to do that. So if I switch between these, does it bring the computer back. It does not.
You restart it.
So, yeah, the problem with that is if you turn the projectors off, they take a while to get back on. So what we're going to do while I'm trying to solve our technical problems is I'm going to write a problem on the board that's actually one that we were going to do later, and then I'm going to call the IT services to see if they can help me out. So this problem has to do with trying to find what speed you need to fire a cannonball at in order for it to hit a target. And so you're told that you have some distance of 20 meters that this cannonball needs to go over, and you have some initial velocity here, or that's what you're trying to find. You're trying to find the initial velocity. And this is fired at an angle of theta, which is equal to 30 degrees. And this is going to go over like this. Now, we're also told, presumably, how long this takes. We're not told how long it takes. You don't need how long it takes. So if you want to fire this this cannonball with some unknown initial velocity, it's going to go 20 meters. Determine what that initial velocity is. Now, another important consideration, and again, it's a little unfortunate because I hadn't gotten to this part, the other part of the slides, is what's happening at the top. So let's talk about this for a second. What can we say about what's happening at the top here?
Where it goes from positive.
Somebody said something? Velocity is zero, close. So it's not that the velocity is completely zero, because if the velocity was zero, if you were a bird up here, you'd be happy to fly by, right? But you know that if you're a bird, you don't really want to be in the path of this at all, right? So something about the velocity is zero. The y component of the velocity is zero. So up here, v sub y is equal to 0. Okay, and that should give you the information that you need to work on this one. And let me try to. Oh, I erased my equations. Or did I? No, they're not up there. Okay, so we had x of t is equal to x0 plus v0 t plus 1/2 a sub x t squared, v sub x of t, and this should be sub x, is equal to v0 x plus ax t. So these are my x equations. My y equations look exactly identical. So this is going to be y0 plus v0y plus 1/2 ay t squared, and v sub y of t is equal to v0 y plus 1/2. Sorry, I don't know why I keep putting that in there. This is plus ay t. Okay, so I'm going to try to figure this out or call somebody to help me. So, persistence with instructional technology, please call 61977. What room is this? So I'm hoping that the slides are going to behave, and I didn't really want to jump into this one because there was a lot to lead up to it. But this was easy for me to put on the board if the slides decided to quit. So we're going to take our chances and go back through and see if we can do this in the right order, and then we'll come to this one at the end, and hopefully we'll be able to do. It's complicated to do now because there's a lot of pieces, but we're trying to build up the pieces. Okay, so it was because I didn't have slides. Yeah.
I'm so stressed out. I'm so sorry.
No, you're fine. You're fine.
I apologize.
No, you're fine. I've been teaching this a while. I'm used to people taking things out on me. I'm kidding. I'm kidding. I bring people to enlightenment too, so it has that certain level of fulfillment. Okay, so let's look at this one now. So this one says military plane is flying at 1,200 meters above the ground at a speed of 200 meters per second. It drops a practice bomb that hits a target after traveling a horizontal distance of 3,130 meters. What would happen to the horizontal distance of the bomb if the plane's speed tripled? This is only a practice bomb, so nobody was harmed in making this problem. Okay, so let's talk about this one. What do we think is going to happen here? What do we think is going to happen here? If we triple the speed, how is that going to change what the horizontal distance is going to be? Or does it change the horizontal distance? Does it fall straight down? No, right? Because it...
If you change the speed of the plane?
Yeah, so what we're thinking here is this plane has a speed of 200 meters per second, and when it lets go of the bomb, it goes about 3,000 meters. And now what we say is we're going to take that and make it 600 meters per second. So is the distance that this bomb is going to go, is it going to be greater than the original distance, less than, equal to? The bomb will just fall straight down, or the affect, and like I said, I'm going to give Laura a hard time about that later, but that can't be determined. Okay, so what do we think? It's fairly intuitive. What's going to happen if I make something go faster? It's going to go further, right? Okay, so let's look at the next one. Now let's consider what happens if the plane's climbing straight up. What's going to happen? What's that? Right, so if the plane's going straight up and then it lets go.
Yeah, it's climbing, so it's going to be straight drop.
Right.
So it would be less.
Right.
Oh no, the bomb falls straight down.
Right. So this one again kind of makes sense, right? Because if this plane is just going straight up and then the bomb, so I'm going straight up and the bomb would roughly fall straight down. You know, I had a little bit of horizontal push. I wasn't going exactly straight up. But if it's going straight up and lets go, it should go straight down. Okay. Next one. This one doesn't have open pulling. Okay, there it goes. Now what's going to happen if the plane is flying at a lower altitude? So instead of being at 1,200 meters, we have it at 1,100 meters. What is going to be the distance that this is going to travel? Should it be greater than, less than, equal to? Will it fall straight down? Or the effect cannot be determined. Okay. So for this one, we could almost consider this same plot that I have drawn here already. So for this plot, let's say that this was the distance of the initial height. This is the 1,200. And then this is the 3,130. Okay? So now if we say that it's lower, what we could essentially do, and you can't do this obviously because you have to move the entire Earth, but what you could do is you could say, well, what happens if I lift the ground up by 100 meters and then see where it intersects the ground? We see that it's a shorter distance. Okay? Was there a problem? No. Okay. All right, coming over here in my space. Okay. So, okay. I have so many copies of the same question. Okay. So now, a stone is thrown horizontally from the edge of a 50-meter cliff with an initial velocity of 18 meters per second. How far from the base of the cliff does it land? And so this is like I said, we're building up to the problem that we were starting before. And this one's simpler than that one is. Okay? So let's go ahead and talk about this one. It's something that somebody had reminded me. I didn't say this in this class, and because I teach both 1051 and 1052, and I know I said it in one of them. I thought I said it in both. But the videos that I'm creating are going to be on my YouTube page, so you can find that by going to Woo Physics. One would think I wouldn't be able to spell physics. 87. Okay. So all one word. Woo Physics 87. Now you know what year I was born in. So that's that. But let's go ahead and solve this one. So where we want to start with this one is considering the picture that we have. So if we look at the picture, this is just kind of the case where something's getting pushed off the table, right? It's going to go like this. Okay, so what are the things that we know? Well, we know that this is some height of 50 meters. This has some initial velocity of 18 meters per second, and that's going to be horizontal. And what else do we have? I think that's it, actually. Yeah. So what we want to find is what this horizontal distance is. We'll call that d. So what is d? Now, if we write down our equations in general, so we say x of t, how's this in the back? Can you guys read this a little bit better? Okay. X of t, and let me make it even bigger. X of t is equal to x0 plus v0 x t plus 1/2 a sub x t squared, and y of t is going to be equal to y0 plus v0 y t plus 1/2 a y times t squared. Okay. Now, let's evaluate this for the things that we know. So we know the initial velocity in x is going to be this 18 meters per second. The initial velocity in y is going to be 0 because this doesn't have any component velocity up or down. We know that we can say that we're starting at x is equal to 0. So x0 is 0. And we're starting at some height of 50 meters above the ground, so y0 is equal to 50 meters. We know that this falls under the influence of gravity, and so we know the acceleration due to gravity is going to be a sub y, which is going to be minus g. And there's no wind or anything to cause any acceleration in the x direction, and so a sub x is equal to 0. So now that we have all of the things that we know here written out, we can plug them into these two equations to make them a bit simpler. And so that's to say that our x of t equation is just going to become v0x times t, where v0x is the 18 meters per second. Our y equation, y of t, is going to be equal to, this is going to be 50, or this is just the y0, so I'll leave it there. So y0, this is 0, and then this is going to be minus 1/2 gt squared. Okay, so now we have our clean equations to work with for the problem, and this is substantially easier to work with than what we started with. So now that we have these two equations, we want to apply some conditions in order to solve for the time that it takes for this to fall. Okay, so in order to do that, what we want to consider is the y equation, because we know for the y equation, the time that it's going to take to go horizontally is the same time it's going to take to fall. And we know that the position when it falls to the bottom here is going to be 0. And so that's to say that for some very special time, let's call capital T, y of t is equal to capital T, the height is 0. Which is equal to this y0 minus 1/2 g capital T squared. We can do a little bit of algebra here, and so we have 1/2 g capital T squared is equal to y0. T squared is going to be multiply both sides by 2 over g. This is going to be 2y0 over g, or t is going to be equal to the square root of 2y0 divided by g. Okay? We okay? No? Okay. Yeah.
In that case, y0 be minus y0?
No, I moved this to the other side. Okay. So let's walk it back a little bit. Let's walk it back a little bit. Okay. Let's walk it back a little bit. We're okay to the point where I had these equations.
Yes.
Okay. We're okay to the point where I had these equations. So what we're trying to do is determine how long it takes for this to fall down to here. And falling down to here means that the y, or the position in the y, is what? It's 0, right? It starts at above at 50, and it's got to get down to 0. So what we want to do is we want to solve this equation for t when y of t is equal to 0. Now, what I'm doing here, I'm introducing this extra parameter capital T, and maybe it's me being a little bit pedantic, but it's not really lowercase t that we're looking for, because lowercase t is something that varies. But I'm looking for a very specific time, which is why I call the time that I'm looking for capital T. But if you like, you can just use the lowercase t. It doesn't really matter. Like I said, it's me being a little bit pedantic. Okay? Yes, a little bit. So we can take this equation and set it equal to 0. 0 is equal to y0 minus 1/2 gt squared, if you prefer just the lowercase t. So far, so good? Okay. So now, from this equation, let's pause a second because I'm doing everything algebraically. What do we know in this equation? We know g, right? G is just the 9.8.
You know G and you know Y.
Yeah, we know g and we know y0. y0 was what we defined here. y0 is the 50 meters. Okay? So the thing that we don't know out of all of this is the time. Okay? That's what we're trying to solve for. And so, in order to do that, I need to get this time to be by itself. So the first step I can do to do that is to add 1/2 gt squared to both sides of the equation. So when I do that, it gets rid of it on this side, it puts it on this side. 1/2 gt squared is equal to y0. Next step, and I kind of combined two steps here, but next step, multiply both sides by 2. Because I want to get rid of the 2 on this side. So that gets rid of this 2, puts a 2 over here. Okay? So we have gt squared is equal to 2y0. We're almost there. We just need to move the g to this side. So divide both sides by g. This says t squared is equal to 2y0 over g. And the last step is just to take a square root of both sides. Okay? And so that's what t is. Okay? It's better? Okay. So now that I have this expression for t, now is the time to plug in the numbers. Okay? So if I plug in the numbers, it says t is going to be equal to the square root of 2 times 50 divided by 9.81. This is about 50 divided by 10 is 5. 2 times 5 is 10. 10's kind of close to 9, and so this is about 3. Okay? You can plug it in to find what it actually is, but I'm just saying this is about 3.
It's
okay.
3.19.
3.19. Great. 3.19 seconds. Okay, so now we have the time, but the thing that we're really after here, this was kind of an intermediate step. The thing that we're really after here is the distance that this goes before it hits the ground. So how can we find that distance now that we know what the time is? Yeah?
You can use the top equation.
Right, we can use the other equation we haven't used yet, right? Because we use this equation to find the time, and then we have this equation that allows us to find what the position is. And so what we do is we take this equation and we plug the time into it, and that's to say that this distance d is going to be equal to the initial velocity, which is going to be the 18 meters per second, times the time that we have, 3.19 seconds, and this is about equal to 54, okay, which is one of the answer choices here. 57, close enough, right? So this is 57. 57.4 meters, okay? Now, if the answer choices were closer together, it told you like it was 50, it was 51, 52, 53, so on and so forth, my approximations wouldn't work very well. But you can do this in such a way that you can get very close to the answer, even if you don't plug in exactly the right numbers. I wouldn't say, don't do that on the online homework, that would really mess you up. But something for standardized tests, for instance, you take the, who wants to go to medical school? A lot of you guys? You can take the MCAT. MCAT has a physics section, and a lot of the questions are going to be kind of like this in the sense that these numbers are actually spread out by quite a bit. So you don't actually need to plug the numbers into the calculator if you know, well, roughly 10 is, if I'm taking the square root of 10, that's basically the square root of 9. It's about 3, right? So there are shortcuts that you can take if you're trying to do this quickly that don't require using a calculator if you don't need to know exactly what the answer is. Okay. Any questions about what I did here? Okay. What's that? Okay. All right. So now we have a demo. So consider this setup that I have here. What's going to happen is this ball can launch out of this cart when it hits a trigger here. And I'm going to push it so it has some constant velocity. We're going to ignore that there's any friction here. It's going to be roughly frictionless. And what we'd like to do is we'd like to predict where this ball is going to land. Is it going to land in front of the cart? Is it going to land in the cart? Is it going to hit the ground behind? Or, you know, there's no way to know. Maybe it does something different every time. Okay? So talk to each other and try to figure out what's going to happen with this one. Okay, so what do we think was going to happen here, guys? What do we think was going to happen here?
It's going to be
B. It's going to get caught. Okay, so let's see if I broke it. Okay, let's see if I broke it. Okay. Silence falls over the crowd. Okay. Okay. Here we go. All right, well, it landed right here. It landed right here. So it was in the middle. And a part of that is if this track is a little bit bent this way or this way, it'll launch it out this way. So I'll try it again. If this doesn't work, I'm going to blame Professor Shepard for breaking it before I got here. Okay. Yeah. Okay. There it goes. There it goes. So it got in there. It got in there. Okay. But I have a video of this in slow motion. So let's take a look at that. And the thing that's really cool about this video is that this is in slow motion, so you can see also some of the YouTube channels I like. Binging with Babish, definitely check that one out. Okay, so this is it in slow motion, and you can really see. Don't need the music. You can really see nothing. Okay, you can really see as they do this slowly that the ball is always directly above the cart. Okay, good, good. All right. So let's hop back into some of our other questions here. So there's another question that's comparing these different plots. Okay. So one, you have some projectile that's following the red path and some projectile following the blue path. And what we'd like to do is to talk about what the difference is between these two. Okay. So take a couple of minutes to talk about this one, and we'll come back together about it. All right. So let's talk about this one. So this one, you have these two plots. You have the red one and the blue one. We want to determine what the difference is between them. So what can we say that the difference is between them based on the comparison of these two plots?
One's blue and one's red.
Well, sure. In terms of the physics. One's hotter, colder maybe, right? But okay.
They have the same acceleration.
They do have the same acceleration. So why do they have the same acceleration?
They start and end the same for everything.
That has to do with the range. Because gravity affects both. These are both moving under the influence of gravity. That's the only force acting on it. We'll talk more about forces later. But that's the only force acting on it, so that's the only thing that can cause the acceleration. And because of that, they have the same acceleration. Now, you said something interesting. You said they start and end in the same place. So that can actually eliminate another one of our choices. So what does range mean, typically? It's like how far it's going to go, right? So if this starts and ends, if the red begins over here and ends over here, and the blue starts in the same place and ends in the same place, what does that say about the range?
It's the same.
The range is the same, okay? So what else do we have left here? We have C. So we could say that object 1 has a greater initial velocity than object 2. Does that seem to make sense? Mm-hmm. Why?
Because it goes higher.
Because it goes higher, right? So the reason why 1 goes higher than 2 is because it has a larger component of velocity in the y direction, okay? And that gives you a net larger velocity, okay? Now, there's actually one very specific case for the angles that these could have the same, that they could have the same initial velocity, but otherwise, well, I have to think about that. But anyway, okay. All right. So next question, we want to say that we have this football, and this guy's kicking the football, and we want to think about this trajectory and these points along the path of the trajectory. And what we'd like to do is we'd like to compare the amount of time it takes to get to point 3 and to get to point 5. Okay? So go ahead and talk about that one. Okay, so let's go ahead and talk about this one. So when we look at point 3, what do we notice about that point 3 in terms of this shape that we have here? That's ultimately a parabola. It's the highest point, right? What happens if I draw a vertical line starting from 3? Yeah, I bisect my parabola, I cut it in half, right? And so if I cut it in half, the time that it takes to go up to 3 is the same time it takes to go down to 5. And so 3 is kind of half the time of the entire travel. And so what that says is 2 times the time to get up to 3 is equal to the time it takes to get to 5. Okay?
I just want to take this one to think not only my friends but the other.
Now, how does the velocity at point 1 compare to the velocity at point 5? Now be careful with this one. Be careful with this one. Okay, let's go through this one real quick because I think we're getting it. So, what do we say about this one? Somebody I haven't heard from. Somebody kind of in the back over here. What do you think? 901, what do you think? There's a 901 right here. Yeah, what do you think? You said B, why B? Right. So in the x direction, what happens in x stays in x, right? So the velocity in x stays constant. Velocity in y is going to change because the acceleration due to gravity. It starts pointing up and then it goes to pointing down. Okay, and because this is symmetric, that means that when it's pointing up at the beginning, it's going to have exactly the same down at the end. Okay? All right. Now what we want to do is we want to compare the y velocity at point 1 to the y velocity at point 2. Wait, hold on. High velocity. We'll hit the. I think we're more ready for this question now that we've gone through some of the other ones. So revisit what we were doing with this calculation and let's try to finish it in the next 10 minutes. Okay.
Sure. All right. We would
So let's go ahead and solve this one real quick. Real quick. So let's draw a picture of what's going on here and label the things that we know and the things that we don't know. So we have this initial velocity, which is ultimately the thing that we're going to try to solve for. We have this distance, I'm going to call d, which is going to be equal to 20 meters. We have this angle of theta, which I'm going to say, which is 30 degrees, okay? So here are the four equations that we have in general, okay? So we have a position equation in x, a position equation in y, a velocity equation in x, and a velocity equation in y, okay? So we want to look at these and determine what terms we have and which ones we can say are zero. So the first thing I can do is I can say that we're going to put our origin right here. So this object starts at the origin, which means x0 is equal to y0 is equal to 0. Okay? Everybody okay with that? Okay. So now what we can do is we can write down what the acceleration in x is. This is just going to be 0. Okay? Acceleration in y is going to be minus g. Okay? Nothing too crazy so far. Now, we know that we're launching this at some angle, and this has some v0 here. And so what we can do is we can make a triangle here, where this is going to be the angle 30. This is v0, this is v0x, this is v0y. Because ultimately, when we look at our equation here, we don't have a v0 anywhere. We have a v0x and a v0y. And so we need to express this in terms, this v0x and this v0y in terms of v0. And so that's to say here that v0x is going to be v0 cosine of theta, and v0y is going to be equal to v0 sine of theta. Okay? So now that we have all of this, let's write down our equations in their simplified form. So x of t is going to be equal to v0x times t, which we said was v0 cosine of theta times t. Okay? Good? Okay. Let's write down our y equation. Y of t is going to be equal to v0 sine of theta times t minus 1/2 gt squared. Okay? Now let's write down our velocity equations. Vx of t is going to be v0 cosine of theta minus nothing, right? This is just constant, right? And this should make sense to us when we're writing the equations like this, because we know there's no acceleration acting in x, and so this shouldn't change. It's going to stay the same. We set it initially to be v0 cosine of theta. It should stay v0 cosine of theta. So now let's write down our velocity in y. Velocity in y is going to be v0 sine of theta minus g times t. Okay? All right. So now we have our simplified equations. What's something that we can do with these equations, or what's a condition that we can bring in here to be able to solve for the time in some way? You know something about this point that we had, point 3, in the football example? What was special about that point 3? It was halfway point, so that's one part that's important about it. Somebody said something about a velocity.
Y velocity.
Y velocity is 0, right? So when it gets to that maximum height, the velocity in the y direction is 0. So that's to say I can take this equation and I can solve for the amount of time it takes to get up to that height. And so to do that, this is just to say y of t is equal to 0, which is equal to v0 sine of theta minus gt. Solve for t. Move this to the other side. Gt is equal to v0 sine of theta. T is equal to V0 sine of theta divided by G, okay? Okay, so that's the time that it takes to get up there. And this is still kind of in terms of unknowns. We don't know what V0 is, but that's okay. We're just trying to relate these things to each other. And so now what we can do, we have this time, and there's another condition or another piece of information we haven't used yet, right? We haven't used the distance that this covers. And so in order to use that distance, what we can say is that this equation, d, is going to be equal to, so d, the total distance, is going to be equal to this V0 cosine of theta times 2 times this time, right? Because the time it takes to go the whole way is double the time it takes just to go up. And so when we do that, we can take this and write it down, V0 cosine of theta times 2 times this time, V0 sine of theta divided by G. And aha, in doing this, we've been able to find an equation that we've combined everything together such that we have only the unknown that we have. Everything else is known. We know what D is, we know what theta is, we know what G is. So we just need to solve this for V0. And so when we do that, I can multiply both sides by G. And I'm going to do 2 at once, so this is going to be G divided by 2. Everybody's okay with that? I'm just canceling my 2 and my G. Okay, so this is going to be dg over 2 is equal to V0 squared times cosine of theta times sine of theta. Divide both sides by cosine of theta times sine of theta. That's going to give me V0 squared is going to be equal to dg over 2 cosine of theta times sine of theta. And now just take a square root. And then we can take our numbers and plug them in here. So this would be, I don't want to do this in my head, because there's a square root of 3 that's lurking in this. But if you plug in the numbers here, you can determine what the distance is, or what the velocity is. And I believe it ends up being 15 meters per second. Okay? All right, so that's going to be it for today. Come up and turn in your homework. We have a stapler now. And then that's it. I'll see you guys on Thursday.